Bless you. So, we stopped worrying, or we maybe started worrying about how computers are taking over the world and maybe we don't trust them. We ended last time by talking about how maybe it would be helpful to write a bunch of tests for our programs that we write. That would maybe give us a little bit more confidence that our programs are doing the correct things, as long as we test them well, get all those corner cases in there and everything like that. But at the end of the day, you can't test everything. Like, maybe you can get any possible input number from the user, and like there's infinite many numbers. How do you know that your program is going to work the right way with every possible input? Tests can't give you that kind of guarantee. There are ways, though, this is where we'll start today, there are ways to make software that is absolutely correct, that cannot go wrong from the start, which is really cool. So there's quite a few different ways. You'll learn about some of these if you end up taking CSCI 26, if you ever decide to take that. This will be where you start learning about how to prove programs correct. So here are some ways to make software correct. One easy way is to just make a couple versions of the same program. Like, you give two different groups the same task, like with these inputs you must produce these outputs, go write a program, and they don't talk to each other, and so they'll write the program that does the same thing but differently. And now you have redundancy. So like if one breaks down, the other you can still trust, and hopefully like they'll check each other. Like, you can have programs that check their answer, making sure that the answer is within the correct range that it should be, things like that. That's possible. That helps make sure that things are correct. Like, so maybe if you make airplane software and you're writing autopilot programs, sometimes you have two versions of the autopilot system running at the same time, and you see if they are agreeing with one another, and hopefully they do. So that's the goal for mission-critical software. Sometimes you make a bunch of them. The standard way of proving software correct is just these mathematical proofs that I've tried to get you into a little bit at least. And if you can do that, you can prove, like, there is a way to mathematically show that your program is always going to do the right thing. It's never going to do anything incorrect. You can prove that, which is really cool. There's also a concept of a program analysis, which is something that I studied in grad school. It's where you specify what it means to have a program running, but you don't actually run it because you don't trust it. You run it in like math. You make a mathematical specification of how your programming language works, and then you check to see if there's any problems by running that analysis. So proofs and analyzers kind of go hand in hand. Lots of math involved there, which is kind of cool. And here's like an example of that. There are some very powerful proof languages. Here's one of them. It was invented by French people, so I think it's pronounced Coq, the Coq proof assistant. And but it's got a little rooster as their icon. And here's what you can do in a place where you can prove things about programs. Like, here's how easy it is to prove some things about programs. I'm showing you that it's not that hard. Let's say that we make a variable in Python, x equals 42. Right? And then we say x equals x plus 1. I think that you right now could come up with a mathematical specification about what is true after those two lines have run, right? I think you can come up with a specification for what it means to give a value to a variable and what it means to change a value of a variable, right? You can prove, right, probably beyond a shadow of a doubt, I think you'd be very convinced that x is definitely 43 here. Does that make sense? It gets a bit more fancy with larger programs, of course, but that's kind of the process. Like, you can specify what those two lines mean in math and prove that x really must be 43 by the time those two lines have finished executing, which is great. Okay, that's pretty nice. Yeah, that's the goal. And then, yeah, so that's like proving and analyzing things. There's also languages where you can like make a specification of what your program is supposed to do, and so there's specification languages. There's just a bunch of examples. We don't have to get into all of them, but in a specification language, you say like you don't give like what's supposed to happen. You say what you're supposed to end up with, like what should be done right now. You specify that in a certain specification language. One is called Z, and then you go and you use some other way, maybe like a proof assistant, to prove that your specification is correct, or the program matches the specification. So that's the thing. Every single one of these things, though, every single one of these ways that make correct software, they require you to make some form of specification. They require you to specify what it means for your program to do the right thing, and maybe in doing that you have to specify what it means to be to do the wrong thing. And so there is one new kind of bug that plops up. If even when you're trying to make correct software, you can make an incorrect specification. There can be a bug in the specification of the program, all right? And so that's what you're proving your program against. So if your specification is wrong, then your program's not going to do the right thing, right? So your specification can still be wrong, sadly. So you have to come up with some good requirements, some good specifications. Like here's an example requirement that you might want to prove. Requirement, I don't know, the output should always be something. The output should always be greater than 42 or something. That's something that you can go off and prove, or that can be your specification. Something like that. Okay? But, of course, maybe you proved your program correct with respect to this, but what if you forgot a digit? Like maybe the output was supposed to be greater than or equal to 142. Then your program's still wrong, but you messed up in a completely different way, which is unfortunate. So you got to get your requirements correct first if you're going to make mission-critical software. Yeah. So that's fun examples that maybe you'll study further one day if you become a computer science major. So there is a way to make correct software, though. And a great example of that is in airplanes. So here's an anecdote. Here's an example of airplane software. So the people controlling the airplanes in the sky, air traffic controllers, they came up with something new. They came up with a device that you put in every airplane, and it tries to figure out if two planes are about to hit each other, which is a very important thing to have in an airplane, I think, these days. It's very helpful. So there's a traffic collision avoidance system box that goes in every airplane these days, TCAS for short, I guess. And it's able to run a little simulation and figure out if two planes are about to hit each other, which is nice. We have that now. And it tells the pilots what to do. Each pilot, it gives them a signal hey, you should do this thing, and then you won't crash. So something like, you got two planes, they're coming at each other. One plane, whee, second plane. And the avoidance system will notice that, oh man, these guys are a little too close, they might hit each other, and it'll tell one to veer off, or one to ascend and another to descend, which is great. But sadly, the first version of that box had a lot of false alarms, planes that were definitely not going to hit each other. It was saying that they would, and so it kind of cried wolf, and people stopped paying attention to it. And they eventually worked out the problems with it, which is nice. But people still didn't trust it, sadly, because of that. So this goes to show that you should get it right the first time, maybe. And there was a crash, sadly, because one pilot ended up following this traffic collision avoidance system. The box told the pilot what to do, and they did the thing. And the other plane ended up ignoring the signals from the box and followed the request of a human, an air traffic controller instead. And so they ended up doing, unfortunately, the same thing rather than opposite things. And they ended up hitting each other. So that was pretty sad. But this box works now well, and after that crash, everybody is now required to disobey the human. They're required to follow the traffic collision avoidance system, the software, and trust it instead, which is kind of interesting. So, any thoughts, comments about that? That's a weird one. We trust machines more now. We are required to trust a machine in certain situations. We must disobey the air traffic controllers. It's cool to think about. We've gotten that good. All right, but I think we also remember some other earlier problems, yes, from last time in our essays and things. So I have a little debate, or I guess personal debate for us. Please go to the Written Nice page, and I'll have you get together with the people sitting next to you after I explain this, but let me clear it out first. And so here's our debate. We've had some examples of software that's good for us, software that's horrible, bad things have happened too, right? My question for you is, do we depend on computers too much? Now we're even required to listen to a computer over a human in a certain case. Please try to come up with one argument that is saying, yes, we do depend on computers too much, here's why. And then also try to come up with another argument against that. Try to counter that and say, no, we don't depend on computers too much. Maybe we should depend on them more, and here's why. Okay, does the question make sense? So try and come up with two competing ideas so that you can get experience thinking about both sides, and then go off, get into groups, say hi to each other, and we'll come back and discuss. I'll give us about, let's say, 4 minutes.
So who wants to write it? All right, so let's write. What do you think we do? Do we depend on computers too much? Here's why I think we depend on it too much. The reason why I think I feel like we depend on computers a little too much because like we always have to rely on them to look for the answer for everything. When we could probably be using a book. We could read books back like in the 90s because people didn't have computers then and they had to use books to get information, to get their resources. And I feel like it wasn't. I feel like not only they had to look for that, they also had to. I feel like that computers like can be great and all, but they can be addicting sometimes. What do you think? What do you guys think? Share your thoughts with me, please.
Computers can create bad habits, but they're also incredibly important because, well, one computer can save millions of trees by not creating a book.
Yes, that's a great idea.
And also computers can calculations that humans can't.
That a book can't do.
Yeah, that a book can't do.
Yeah, because like the math books don't even make sense.
Yeah.
It can create bad habits, such
Yeah,
as Twitter.
Instagram, because I made like, because guess how many posts I made? I made 271 posts. I'm pretty good on Instagram. I'm pretty loving being me on Instagram. Good. So what else do you think? Let's think about what else it's important. Well, sometimes computers can always give you the wrong information because the internet doesn't always tell the truth, you know.
That's true.
Yeah, because the internet can have like can make the internet can also be dangerous because you can get viruses. There are some sites that can pretend to like they're trying to help you. But they're actually going to give you a virus and just give you false information. It could really affect your computer. What else do you think? But I think computers are good because they can help us learn more information about stuff. And by looking at reasonable sites and help you look for what you need so you don't have to go in stores and get something. You don't have to go in stores and order it on the computer rather than going into a store and not find it there, you know. What do you guys think?
I like my computer.
Don't go where they can spy on you.
Good for them. They can see that I'm playing Minecraft.
Access to things, we can learn more about history. It helps people who don't like reading to listen to audiobooks. And seriously, I don't like reading. If I didn't
One
have
more
audiobook
minute.
as one, I probably would have failed that class.
Oh, I did pretty good in my English class. I did pretty good. I'm pretty good at English, you know. I know how to write essays. Pretty good.
I mean, I'm good at English, but just I don't like the reading portion.
An audiobook. Like maybe she should do Dork Diaries. Like what do you have to do an audiobook for?
No, for the essay we're gonna write, because I saw the thing that I'm gonna try to find audio for me to read the book thing, so I gotta focus on it.
Wait, for this class? Wait, I didn't know you had to do an audiobook.
No, no, I was just saying like there's the
Kenny listens to the audiobook rather than read.
Okay, that explains it.
All right, that is my timer. Let's come back and see what we're thinking. Let's see why we love and hate computers. What are our thoughts? Where did my start menu go? So thank you for making your submissions. Let's take a look. We depend on them too much because just looking through the past, an example is like writing assignments. I remember having to handwrite essays in elementary school. That's true, yeah. Have we forgotten how to write, maybe? I know they don't teach cursive anymore because of computers. Isn't that a thing? Did you guys learn cursive in elementary school like I did? They stopped that. You did? That's a new thing, right? Still takes a form of a human input in things due to sometime technology not behaving. Yeah, so sometimes you still need the human for certain things. We're trying to phase out humans, but like what if we run out of electricity? Who knows? We're still going to need to train humans to do certain things, and I think I can see where Group 50 is coming from there. So nice. Group 51, definitely social media. That you could think of that as a problem. Yeah, computers can help create bad habits, but on the other hand, they can they're invented to do math very quickly for us, and they're really good at that. They can work much faster than any human possibly could. And that's true. If you want to read stuff online, you just buy like a Kindle or you buy like a laptop with a good screen and you read a bunch of books on that and then you've saved a lot of trees. That's true. I like that thought. Let's see one more group. Too much because we use them for everything these days, right? Like I never go to my bank. I always interact with it through the app. Like maybe that's not good. They don't know who I am. We rely on cars to get around, especially in Fresno. And yeah, we all use calculators, and maybe we've forgotten how to do basic math because of it. But is that a good thing? Is that a bad thing? We have no clue. But yeah, on the flip side of that, they're very efficient, and they can help us do some things that maybe we couldn't do with just humans. Yeah, those are great thoughts. Any comments? Last questions about that? Thank you for thinking about that for a little while. Good critical thinking example, I think. All right, let's see. Where was I going with this next? I'll get out of that. Yeah, so here are my thoughts. I just thought about some things, and then we also should probably take this as a question back to our boys. So let's see. With that air traffic controller example, at least, that's like great because maybe we should depend on computers more. And that was a great example of like they're going to save lives if we trust the computers these days, which is nice. But then, should we be using them at all? Let's ask like Kant. Kant would pose the question like, should we always like use a computer to solve a problem if we can? And I think Kant would be again proponent of individual freedoms. He's like, if you don't want to use a computer, you don't have to. So I think Kant would be definitely pro whatever you want. So you don't have to use a computer if you don't need to or if you don't want to. And then maybe a more utilitarian perspective would be, yeah, computers these days, if you don't know them, like most jobs require the use of a computer, so you better learn how to use them. And that's the only way you can be a functioning member of society these days or something, which is maybe a bad thing, but that's where we've gone. So yeah, interesting ideas. Computers, like the TCAS example, they're being used today to make us potentially safer. And let's think about some more examples of that. So like in your car, I think everybody with a car made after like the late 90s has those automatic braking system things in their car, ABS. Those exist. That lights up when we turn on our car, right? That's very important. That's a little computer like pressing the brake, pumping the brakes for us, because you used to have to do that before that existed, right? So that the wheels don't lock up and you skid. You also have a check engine light. Mine came on this summer. That was no fun. But at least your car can tell you when something's wrong rather than it just breaking down one day, right? Hopefully you get to it before the problem happens. And then airplanes, of course, we have autopilot these days to save the pilot's energy, and then also the traffic collision avoidance system, which is great, keeping us safe out there. A lot of people have really gotten into home security systems these days. It's become cheap to put a camera around your house. That's the thing. Before that, we had to all buy dogs or something, and that was how we kept our home safe. But now we can record stuff. That's kind of cool. Our phones are all locked with passcodes or like our face or something like that, which is nice. Keeps our private information private rather than just like putting stuff in a safe that somebody could maybe break into in our house. It is encrypted, which is cool. And that leads into like websites where you buy stuff and like using your bank online, where you go through this encryption process to talk to the other side, to talk to your bank, to talk to Amazon, and like everybody turns on, like even the school has forced two-factor authentication on us teachers at least already. And so if I want to log in on Canvas, I have to get out my phone now and it makes sure that I'm me and nobody else can look at your grades or something, which is kind of nice, which I think is a little bit that has to do with safety, right? So yeah, computers are doing good in certain aspects of our lives, I would say. I am, though, biased as a computer scientist. Yeah. Any questions about these slides before I switch gears to a completely different topic? We're in between things right now. But if we're good, let us move on. Oh, I can stop this before I forget. Let us move on to artificial intelligence. This is a very fun topic. I'm glad that I get to teach it a little bit to you. But there's a lot to talk about. It's gotten a lot more fancy. Maybe I need to update my slides even more. But let's start by talking about how computers are fast. All right, let's talk about something called Moore's Law. Let's talk about this person. So Gordon Moore, by the way, the person who made up this thing called Moore's Law, he came up with this idea way back in the 60s, which is kind of cool. And it answers this question about, like, how fast are computers getting faster? That is a question that you could ask, and it makes sense, I promise, which is kind of nice. So, yeah, this dude, Gordon Moore, co-founder of Intel, came up with this idea, or he saw this trend back in the 60s, and it's more or less held true up until now. It's starting to not be true too much anymore, though, okay? So we've hit a wall, and we'll talk about that too. But what this guy observed is that the number of transistors, remember those on the first day of class, the number of transistors that you can shove into a chip tends to double every about 2 years, okay? And so that's nice. You can plop twice as many transistors on a chip 2 years from now. And for a very long time, that was a very true statement, and they even did maybe a little better than that. And if you double the number of transistors, that also tends to double processing power. So for a long, long time, it meant that 2 years from now, you'll also have a computer twice as fast. So, like, why make your software faster when you can just wait 2 years and it'll run twice as fast? So that was a thing back then. This is definitely not true anymore. But transistors, for the most part, for many decades, they correlated with the speed of a computer. But eventually, we ended up running into like a power wall for processors. You can only shove so many transistors into a certain amount of space and then ever hope to dissipate the heat that comes out of them. So we could make CPUs that are faster than like 4 gigahertz or so. That's where we've like plopped it. That's where we've what's the word? That's where we've plateaued. Like, you don't see a processor usually that's faster than 4 gigahertz. Because if you made it faster, it would consume a lot more power and it would also make a lot more heat. So it would be very, very difficult to cool that. That's why we've stopped around there. But for the most part, we still see this trend with transistors. There's another way to solve the problem. Like, I don't know, year 0, there's 1 transistor. Year 2, there's 2 transistors. Then 4, then 8. It's like an exponential growth. Whee! Something like that. And that's what's happened. There's also another wall that we're about to hit. By the way, power limits. The reason we were still able to double the number of transistors, we just made multi-core processors. That's what happened in the late 2000s. That's when those started becoming things. So we kept the same 4 gigahertz processors, but we just put a bunch of them in a certain spot. So we still doubled transistors, but we're also about to hit an atomic wall soon, which is fun. So this is going to be the end of the line for Moore's Law, sadly, because you can only make transistors so small before you start like getting into quantum issues, like electrons start leaking, and so transistors stop being able to do the right thing. So that's kind of fun. But Yeah, more or less these days, because of Moore's law, we want to try to keep it working. We put a bunch of processors on our processors, and so maybe you have like a 4-core processor inside of your computer. I think that's what this laptop is. And so each one of those can do its own thing at like, I don't know, 2.5 gigahertz, if you know what that means. This means like billions of operations per second. A 2.5 gigahertz processor can do 2.5 billion things per second, 2.5 billion additions, for example. And here's a cute little graph of Moore's law. On the x-axis, we have time, so early days of CPUs. And then on the y-axis, we have the number of transistors, and this is a log scale. So if you see a line trend, and we sure see one of those, that means it's exponential growth. It is doubling like we thought. So Moore's law really did hold, and it held for a very long time, so this is kind of cool. You still see the trend line. It's kind of fun. So let's zoom in and see how far we've come. Whee! So some of the very first Intel processors, they didn't even have 10,000 transistors. Crazy to think about. And then we have some very famous ones like Motorola 6800s. Those powered some of the first personal computers. Very cool. I forget like when the first game consoles came out, but I think this was in like the original Nintendo NES or something, one of those. And yeah, we were on the verge of like by the 80s, 100,000 transistors, which is really not too many. Our processors were quite slow, but just you wait a couple years and suddenly it starts doubling. It starts doubling, which is really interesting to think about. The processors that are in our phones these days are ARM processors, and those started back in the 80s, and their selling point was they're just as fast as an Intel processor, but they have like significantly fewer transistors. So that was a selling point back then. It's cheaper, but just as cool. You'll talk about that more in CSCI 45 if you ever take that class. And then, yeah, eventually we start getting into the millions of transistors by the time we get to the 90s, the early 90s. And computers still getting twice as fast. They're still single-core processors. We end up with the Pentium processors, which are very famous. And eventually we hit that power wall around the late 2000s, and so you start seeing the word core in these processors, and that means they're adding multiple cores, multiple execution units. And now we're getting close to 1 billion transistors too. That's how they kept it all doubling. And now these days, like giant server processors, 72 cores, we have billions, tens of billions of transistors, and yeah, it'll just keep going up. That's how they're solving the problem right now. They're doubling the transistors by just making giant CPUs and putting a bunch of cores in them, if you know what that means. So yeah, that is Moore's law. Computers have been getting faster for a while. Now if you have programs that can be run at the same time in multiple places, you can still make them twice as fast because you're adding cores. Yeah, any questions, thoughts about that? Have we made our own computer? Do we know what gigahertz means? Have we heard that word before? Computers are getting fast, and one thing that they're really good at, especially one thing that's very parallelizable, which is good for GPUs and multi-core CPUs, is artificial intelligence and machine learning. So let's talk about that. All right, so I'm going to try my best to teach you how computers think and how good are they at thinking by themselves. This is, of course, this whole topic can span multiple undergraduate and graduate computer science classes. So I'm only going to give you a taste. Hopefully you like what you hear and you'll go and study it some more later. So let's first define artificial intelligence. Like, what does that even mean? It's just when computers or machines think in some way, for some definition of think. So here's one definition. Artificial intelligence is when a machine is perceiving its environment, so it's taking in info that it was programmed to take in, has like sensors and stuff, and it's making choices based on that information to achieve the goals that were programmed into it. So it has some goals, and it's trying to achieve those goals based on its environment, and it's able to freely make choices to achieve them. So that's kind of cool. It's a very utilitarian idea, I think. Artificial intelligence is a very broad field, so that's why there's so many different versions of it. Like you might think of like when I gave that definition, you might think your mind might jump straight to a robot, and that's definitely a subfield of AI. There's those Boston Dynamics robots that you've seen in funny YouTube videos where they like hop along and dance and things. Go watch those if you're interested. But there's also, of course, machine learning. I consider that to be a subfield of AI, where you're doing face recognition, so your iPhone can unlock your screen. You're trying to make a self-driving car or stuff like that. You're trying to generate text, generate images, and those are usually these days programmed with a type of machine learning called a neural network. That's definitely won out, especially in terms of like big data processing and generation and stuff like that. But there are other kinds of machine learning, of course. That's just one thing, but it is definitely won out recently. And yeah, at the end of the day, achieving your choices, predicting things, it really all goes back to statistics. So honestly, artificial intelligence or definitely machine learning, it's just a fancy word for applied statistics. You have to be really good at statistics if you want to understand machine learning, artificial intelligence. It's just trying to predict stuff, and what better way to predict things than by doing statistical tests? Okay, that's the goal. So if you like statistics, you might enjoy artificial intelligence, and it might make a lot of sense to you. So I just have a bunch of examples, and I'm going to try my best to teach you some things about AI. I have a fun website example to go to today, and we'll start there. So here are some examples of artificial intelligence that I'm sure you know about, but let's try and talk about how they are made, at a very high level at least. So one of the original uses of artificial intelligence that like people started to have access to were those old digital cameras where like it would draw lines, it would find everybody's face and draw little boxes, and then it would also notice if somebody blinked. Have you seen those before? It's been a long time, but that's probably the very first example that I can think of artificial intelligence. Maybe your parents know about these things, but like the original digital cameras, you have a little viewfinder, and it would notice that somebody was in the viewpoint, in the viewfinder. Like there is this person, and then it could track their eyes and notice if they're like blinking or not. So it's able to draw boxes around their eyes then. And it was helpful. It's like, oh, I noticed that somebody blinked in this photo. How did it do that? How does it know? How did it learn what it means to be a face and to know if somebody blinks? So let me try and teach you how this artificial intelligence software, this very old camera, got made. All right. So in general, let's talk about how machine learning works. It's a 3-step process, or at least that's how I want to introduce it to you. Okay. So the first step, if you're going to make software that is made using machine learning, if you're trying to solve a machine learning problem, have a computer think for itself, like notice blinking or something, the first step is usually the hardest, it's to make a giant bucket full of training data, which is what we call that. You need to, for this example, you need to get a giant amount of images, okay? And usually you're going to label that data so that you can your machine learning program, which is called a model, by the way. That's just another name for your machine learning program. You're going to label your data so that your model can learn the labels, essentially. So, for example, if you want to notice faces and images, you need to give, as your training data, a bunch of pictures of people's faces and boxes drawn around them and labeled. So you got a bunch of images of faces, and then also you need a bunch of images of non-faces as well, like images of airplanes or something. That will be your training data for this particular model that we're trying to train, for this particular machine learning program. Does that make enough sense? And if you label that, then a machine learning algorithm takes over and starts learning what it means to be a face, learning what it means to not be a face. Okay? Because we don't want it to like hallucinate and think that there's a face in every airplane or something. So that's why we got to give it stuff that is not even something that we care about. So that's your training data. And you label that, like, here's a picture of a person, here's where their face is, I've drawn a box for you, and this person has their eyes open. And then you give another image, like, here's a picture of a person, here's where their face is, it's over in this corner now, and they're asleep, so their eyes are closed. Or they blinked. Figure that out, all right? So that's the first step. You need a bunch of those, and that's why we'll talk about that at the end. That's probably the hardest part. You got to get your hands on a bunch of training data. The better the training data, the better the model. And then the next step is to train that model. It's called training data for a reason. You train your machine learning program using some type of machine learning technique. All right, and one very popular technique models like an artificial brain, and it's called a neural network. It's got a bunch of programmed neurons. That's how we think brains work, right? So it's got a bunch of little neurons that pass around information, and it's just shoving numbers along some pipeline. And this is how machine learning, this is how a neural network works. It's like shoving numbers around here, and eventually like there's an output neuron, and like if the number is high enough, then it thinks like, oh yes, maybe that was a person, there's their face, and their eyes were open or something. So it's all numbers at the end of the day. I'll try to teach you a little bit more about this in just a second, but that's the idea. You're going to train this model on your training data, and at the very beginning, like your artificial brain knows nothing. It's got a bunch of neurons that are not like wired up very well, and so it's just going to be hallucinating. It's going to be horrible. Your model is going to be horrible the very first time, but you keep running it, and you keep on telling it, oh, you were wrong in this way. Oh, you were wrong in this way, and eventually it keeps getting better. It can figure out, oh, okay, that's the whole point. Machine learning algorithms are cool because you're allowed to refeed in that training data, and the model learns from its mistakes, which is weird to think about. I can't really explain that very well until you're ready for a upper division computer science class. But there's a certain kind of algorithm that can be you can feed data back into itself, and it will get better over time. Okay, so it learns. That's what machine learning is. And then finally, you took care to test your model. You took care to take some of your input data, your training data, and set it aside. You didn't use it to train your model with, because you didn't want your model to memorize things. You wanted it to notice and figure out what faces are. So you test your model on a separate set of data, something that you did not train on, so that it couldn't memorize anything. And then you see if it actually did things right. So that's how that's the last step. It's like, did it actually learn the thing? That's the 3-step process to machine learning. Get a bunch of training data, train a model. Over time, it gets better and better on the training data, and then have some testing data that's separate to make sure that your model wasn't just memorizing the answers. Okay, that's a hard problem too. So step 1 is actually the hardest. With a big enough neural network, you can learn pretty much anything these days with enough training data, and it's very hard to get a good amount of training data, and training data that's like well labeled and things like that. And so if you've used Google Photos before, do you remember that it used to be free? It would store every image you could possibly want to upload. Google was happy to hold it for you. Nowadays it's paid, but it used to be free because Google was trying to train their machine learning algorithms. And now they're good enough, they don't need your images anymore. But they wanted that, and that's why they made it free for a little bit. It's kind of funny. Any questions about that? This is definitely a complicated topic, but maybe we've heard some of these terms before, especially now that AI has gotten a bit more popular. If we are happy, I would like you to take a couple minutes to try these places if you have not seen them before. The first place I want you to go, this is just one website that automatically generates images. If you've never done this, you need to do it now. It's called crayon.com, but it's spelt with AI in the name, so they changed the word a little bit. So crayon with AI in the middle. Crayon.com. Go there for like a minute or something, and here's what you can do. You can just give it a little prompt, like, I don't know, what should I ask about? Maybe a cat sniffing a flower with a rainbow in the background. And you could have it generate like art, a drawing, a photo, whatever. But you can give it any prompts within reason, and it will take a little bit on the neural network will try and figure out what you just asked for, and it will try to turn that into pixels. So that's one very fun idea.
Okay, it's taken a while.
Yeah, it takes a while to think. it's a complicated process, but it'll give you some options too. And yeah, so hopefully this has definitely become more popular. But if you've never tried it, now's the time. I'll give you a minute or two to play around with this, and then I have a better website that actually kind of tells you really what a neural network is all about. And I'm excited to get us there. But take a couple minutes to play around with this. And so yeah, somehow this neural network is able to figure out that, oh, okay, this is what it means to be a rainbow. This is what it means to be in the background. This is what it means to be a flower. This is what it means to sniff. Like, some of these are really good. It was kind of funny. That's the idea. That's not so much a flower, but it's trying really hard. And sometimes the cats look a little weird, but that's a good starting point, I think. Yeah, and so, are there any questions about this? We've probably seen this before now, but just imagine a couple semesters ago when I was showing my students this website. They were blown away. So yeah, try another image for a minute, and then in the background, let me try and kind of explain what's going on here. So this is a text-to-image generation algorithm that's running right here. Some sort of machine learning thing. What they needed to train, right? What do you think the training data was for this? Very important to think about. It was a bunch of prompts. It was a bunch of text describing images, right? That's what you would have trained this with. That's the only thing that you need. It's like, all right, because that's what it learns about. That's what it learns what cats are. There's some text describing a picture that you gave as your training data. And it's like, oh, I see what's in common between the pictures with cats in them. I know what a cat is. And so that's how it learns what rainbows are. You just give it a bunch of images and prompts that are associated with that image, descriptions of it, and then it's able to pick that apart. And so eventually it learns like what sentence structure means, what background means, all that stuff. Because it appeared in the training data. It was just a bunch of text and image pairs. And yeah, that's pretty much it. Yes. With enough time and enough training data, I think you can imagine how much that would have taken. We're talking insane amounts of images and descriptions of images. You can figure out how to fill in pixels and make images. Make pictures back for you in response to your prompts. Yeah. Any questions about that? Does that make enough sense?
It's pretty cool.
So it's not magic, even though it feels like it is. It's just you gave it a bunch of training data, a bunch of pictures with prompts or descriptions, and it's able to learn what a cat is, learn what a rainbow is, and it can run in reverse. Like, you give me a prompt, I will come up with what I think the best image in response to that prompt is. And it's able to think that way. That's really cool. All right. And so this is using a neural network in the background. This cool thing, this cool artificially created brain. I'm getting there. It's using this artificial brain, and this next website is going to teach you how that artificial brain works. Here's an example of artificial neural networks. If you go to playground.tensorflow.org, please, that's going to take us to a very cool place that actually is going to teach you what it means to be a neural network. And so please go here. I'll keep it open and big because it's a longer word. But just hang out once you get there. Once we're all there, I'll explain the website. It's a little weird. But it's a graphical representation of what a neural network is. And it lets us learn some stuff. All right. All right. So on this website, there's a lot of stuff. There's a play button. There's a lot of things down here. This is the neural network. These X's and things. These are your inputs. These things called features are called your inputs to your neural network. And then you have some layers to your network. Here's some neurons, artificial neurons made in code. And then there's what's called an output layer. There's a bunch of little layers. And then the last one is called the output layer. It gives back an answer. So this is a very simple machine learning problem, just to teach you what a neural network is. It's the goal of this particular example is to distinguish the orange dots from the blue dots. Okay, to kind of see how you might describe to a computer what's the difference between the orange dots and the blue dots. But the goal of this neural network is to learn learn the difference between orange dots and blue dots and like cut them off and predict. Like, oh, okay, you give me this coordinate, I will tell you that it was a blue dot. You give me this coordinate, I will tell you that it's an orange dot. Does that kind of make sense? So the input is the coordinate of like the dot or something about the coordinate, and the output is whether it should be orange or blue. Okay? Like, I'll learn what it means to be an orange dot or a blue dot. That's the goal. And these little neurons are hooked up so that they're passing around information. It's like, all right, maybe these guys, they feed into the next layer of neurons, and it does something with them. Like if this held a number, all a neuron is doing in a neural network is holding on to a number, and then it's like passing along those numbers. It's like this next neuron, this next layer gets those two values, like adds them together, and then does some nonlinear function on them. That's how it learns. That's kind of cool. Maybe this one only takes this one and does something special with the 2.0, and then it kind of feeds it on down the line. That's kind of what's going on. It's combining the data in a certain way that eventually it can learn from. And so, honestly, the answer, like you're trying to make it a big long system that either gives back a number between 1 and -1. If it's closer to 1, it thinks it's blue. If it's closer to -1, it thinks it's orange. And that's what it's learning. So here are your features. These are all the inputs that you could get. Right now it's hooked into the x coordinate of the dot and the y coordinate. X2 stands for y coordinate because there's usually many dimensions. There's more than just two. This is hard to read. This is the x coordinate squared. x1, 2. This is x2 squared, the y coordinate squared. This is x1 times x2. If you wanted that as part of your neural network as an input, you just click it to highlight it. Here's the sign of the x coordinate. That could be part of your input. And here's the sign of your y coordinate. All right? But yeah, and here's a bunch of neurons, and then its job, if you press play, it's going to try and learn the difference between orange and blue dots using your inputs, and it's going to learn weird things. So it learned that separation, and it's telling us how good it's doing. Loss means the percentage incorrect, and so it's almost perfect. Okay? That's kind of cool. Does that make any sense at all? Are there any questions about that?
It kind of looks, it's a little bit confusing to understand.
Yeah, and so you can by the thicknesses here, you can see which neurons are more important. Like apparently these two neurons in the middle here, they're sending a lot of blue data. They can kind of figure out what it means to be a blue dot more than the others. Like maybe this one down here is learning a lot more about what it means to be an orange dot. Something like that. So that's the idea. That's what's going on there. So yeah, play around with this. Like try these other data sets. You can add more hidden layers, add more output layers. Try and get the minimum possible, because the more layers you have, that's more complicated of a problem to solve. But try and see if you can get this to learn the difference between like this checkerboard pattern of orange and blue dots, or this separation pattern of orange and blue dots. There's about 2 clusters over there and over there. Then see if you can find it, if you can figure out how to solve this swirly pattern. That will be the hardest one. But try and get the minimum number of hidden layers and neurons and output things. Figure out the easiest way to learn these things.
Pattern, yes.
You can do it with fewer neurons even, but just playing around and like hovering your mouse over should teach you a little bit, I think. So take a few minutes to try this, and I'll show you the ultimate answers, the best ways to possibly do this, and we'll learn a little bit about neural networks. And help each other. So yeah, take a couple minutes to play around with that. Maybe change the inputs. But just based on the coordinates, some weird input that has to do, it's not weird, I guess. You're getting the coordinates in some form as inputs, and then the output is whether it's orange or blue. You're trying to learn the difference between the orange dots and the blue dots by messing with things. And when you press play, you'll see that it's horrible at first. It doesn't know anything, but then it starts learning the difference, using your neurons to learn things. learning numbers and weights, really. Like this neuron has more weight than other neurons, etc., etc.
So we're trying to make it look like the one like up there. Like
It's any, you can pick any of these data things, and you're trying to get very low loss when you press play. And you're trying to get it to discover the difference, draw the difference between the orange and the blue dots in each of these cases.
Well, I got low loss on one.
Try the others.
That's the spiral one. Looks at it.
And also, try and get it with the fewest number of neurons, because the more neurons, the harder this is computationally. The more it costs to run this machine learning program. Alright, so definitely you can play around with this more, but let me show you the secrets. Because at the end of the day, it's just doing math, okay? If you're trying to learn this, what is the separation between the orange dots and the blue dots? It's like if you could just draw a circle around the blue dots. Everything inside the circle is blue, everything outside the circle is orange, right? That's essentially it. So what's going on when all this information is being passed along to neurons? They're all just like, they're summing together the inputs somehow, and then they're doing something based on them. So if that's all you knew, really we just want to have the neural network learn the equation of a circle. Do we remember the equation of a circle from math class? No. X squared plus y squared equals r squared, right? So if I wanted to learn that, let's give it the x squared coordinate and the y squared coordinate, and that's literally all we need. 0 hidden layers. Play. It learns a circle. Does that make sense? It's just learning how to make the circle. What should be the, like, what's the constant out in front of this x, the constant out in front of this y, etc., etc. That's the easiest way to do that. If you knew your problem, like this is why the machine learning engineers make the big bucks, because they can figure this kind of stuff out. Saves your company a lot of money if you don't need any extra neurons, right? So that's that one. What about this one? What's the easiest way to learn this? Learn a checkerboard pattern. It's more or less the quadrants, right? Let me make this go away. It's blue if it's in the first quadrant or the third quadrant, where there is they're either like x and y are both positive here or they're both negative here. And then here in the orange dots are in the other quadrants where there's one negative coordinate and a non-negative other coordinate. So honestly, if you just multiply the two coordinates together, that's all you need. Just figure out which coordinate, which of the two quadrants you're in. So that will learn the checkerboard pattern, at least for this particular checkerboard. Does that make enough sense? That's how you learn that one. These two, this one's super easy because it's just a line. What is the equation of a line? It's something involving, it's like y equals mx plus b, so it's like here, y and x, give those, and have it learn something based on that. You can learn a line that splits the two. So that's simple. The spiral, that's a very complicated one. So honestly, that's the one where you throw computers at it. You just give it a bunch of hidden layers and give it a bunch of neurons. It's a very non-linear problem to solve. And so you just have it, you just give it a bunch of information and it can approximate this eventually. But it's very slow. You see how it's learning much slower. Epoch means it's running all the training data once. So it's going slowly but surely, and it might eventually learn something. Or I might have to restart it and give it even more neurons. But yeah, when it's not easy like this, and usually it's not easy, it's just throw large neural networks at the problem. And that's what they're doing for this image generation stuff and the text generation stuff. They're just throwing giant neural networks at the problem, and eventually it's able to approximate some really cool things, like human text and drawings. But yeah, it takes a while to train, but see how it's getting there? The loss is getting better and better, and it'll probably max out soon. But you can see, like, this is really helpful. what each of these neurons are doing. They're learning. The first layer is learning some facts, and these are like the most important facts. Orange things over here, blue things over here. This one's learning something about this circle right here. And then the next layer are combining the previous layer to learn other things, more information. And eventually, like, combining all that information in weird ways gives you something like this. And it gets better and better and better. It's trying to learn a spiral. Okay? Yeah, I think that's all I have to say. Any questions about that? Yeah. Not necessarily. Sometimes for this kind of problem where there's no mathematical equation for this spiral very easily, then you're kind of forced to throw more neurons at the problem. And fewer neurons, like, for example, if I just gave it x and y squared again, all that could ever hope of doing is learning a circle. And so it could never learn the spiral. Does that make sense? Yeah, sometimes you need the extra room, the extra thought space. So yeah, that's neural networks in a nutshell. I hope that made at least a little bit of sense. Try playing around with that more. I encourage it. But yeah, for the rest of the day, I just have some more examples of like use of AI. So one popular one is like you're going to make a robot and it's going to work in the factory all day long. So machines are great. Like if you're going to make a car, machines are great at doing the same thing over and over again, like adding a bunch of numbers, moving this part from here to here. They're also really good at not failing, right? And they can work a lot faster than a human, which is kind of unfortunate. That's why a lot of factory jobs are going away from humans and to robots, which is potentially a bad thing for humans. But that's something that's very easy to make, especially these days. It's getting more and more cheap to make machines that can move stuff around and do very precise things, more precise than a human possibly could. All right, that's the goal. And of course they're expensive. Just think of some special, like, I'm going to make this specific type of machine that works on this specific type of car. That costs a lot of money up front. But also, I mean, think about the number of humans you don't have to hire anymore once you make that. So there's definitely a tug and pull there, and robots are starting to win out. So that's a societal problem potentially. If you've heard about the game Jeopardy before, maybe you heard about the Watson computer, the supercomputer that was playing on it once upon a time. And this is what I had in my mind when somebody asks me about, like, what does it mean for computers to think? It's like, this is a great example. Like, Jeopardy is just a game where you could be asked anything potentially, and so a computer has to know potentially everything. Okay, so Watson is a supercomputer. It was made by IBM back in 2005. What it does is it uses what's called natural language processing, which is a subfield of artificial intelligence, that can like look at the text of the Jeopardy question and like figure out like what it was asking and look at its giant database of information for the answer. So it's able to, what natural language processing does, it's able to break down the sentence into like a subject and a verb and all those things and figure out what it's asking. That's all natural language processing is at a high level. And then what Watson did is it had all of Wikipedia saved inside of itself and everything else that you could possibly want to use for Jeopardy. And it would parse the sentence with its natural language processing abilities, consult its database of the entirety of Wikipedia, and come up with some answers. Like, here's a possible answer. Answer 1. Answer 1. Answer 2. Answer 3. And it would give some weights to its thoughts about those answers. It's like, I think with like 95% probability it's this one, 85% probability it's this one, and maybe 5% probability it's this one. Something like that. That's my confidence level. Could be one of the first two, maybe. The third one is potentially the case, but not too probable. And so just go look it up on Wikipedia if you're interested. It's very cool. It beat all the humans because it could think a lot faster. It sees the picture of the question and it's like, all right, I got the answer ready. It's like it comes down to how quick you could press the button, and of course the machine can press the button faster too. So that was Watson. Definitely look into that. That's a fun example, I think. There's also a great long history of computers. This is like This is probably one of the reasons the machine learning field was created, the artificial intelligence field was created, so that people could play chess. All right, so chess and Go these days as well. So back in the 90s, that was the first time we made a machine learning program that learned how to play chess, and it beat the world chess champion at the time. Crazy. That was amazing. Took the world by storm, apparently. And so that was cool. Go is also a newer game. No, it's not a newer game. It's just a newer solved game. It's more complicated than chess, but very similar to chess in certain ways. And there's just a lot more possibilities of like how the game could unfold. So it took more processing power. And so in 2017, we finally made a machine learning program that could beat the world champion at the game Go. And so feel free to watch that if you'd like. But these are great examples, and people flocked to them when they were learning about machine learning for the first time. Very popular examples and very fun ideas. A great thing about chess and Go is that the rules are so clear, right? You know all the valid moves on a chessboard, right? You can just program that very quickly. That's not hard. So, and you can program what it means to lose the game, what it means to have a checkmate, right? So you can program the rules of chess very easily, and then your program doesn't need any training data, right? It doesn't need any prior information because it knows how to play the game. Like, these moves are possible. And so this is crazy to think about, but the way that you would train a chess machine learning program or a Go machine learning program is you have it play itself. And it would learn the best moves based on that. It doesn't need any other information, right? Because it can play millions of games over a few days or billions of games over a month or something. It can just keep playing and figure out the best possible moves. So essentially what a machine learning program is doing, if it's playing chess or something, it's got the game board, and it's thinking very hard about all the different ways that the game could progress. It's like it's drawing a bunch of smaller chessboards, right? It's thinking about, all right, if that move gets made, here's what the board would look like. If this other move gets made, here's what the board would look like. And it's coming with probabilities of like, maybe this is the best move for this person, so I think I'm going to explore this path because I think they're a good player, something like that. And so like after this move, maybe there are some other moves. What moves could be played after that? So it's trying to draw this big long tree of possibilities, and it can like solve for the best route that it can control. That's pretty much it. And you can have it play itself, and it can figure out, okay, yeah, I see that like in this situation I should usually do this. In this situation I should usually do this. It's really cool to think about. But yeah, that's chess and Go. Great examples of computers learning. Any questions, comments about any of that? I think that's the last little topic of the day. It's just cool ideas in my mind. Go look this up if you're interested. Go and watch people losing to computers. But if we're good, I would like to release your next essay now, and then I have one last slide about the essay. So where was I? Here. So here is your essay. It is about fallacies. I promised that this was coming. It will be due week 12, so 2 weeks from now, because it's a longer essay. This is your first 1,000-word essay. Okay? Don't get too alarmed because you're going to be copying a lot from the internet. Okay? Here's the goal. All right? First of all, you need to read these directions. I don't want to give you a low score. You have to. You must read these. Otherwise, if you do it wrong, you're going to get graded badly. Okay? There are a lot of requirements for this essay, but I think it gives us a very cool outcome in the end. All right? What you're going to do for this essay is you're going to find 5 fallacies on the internet, in social media, most likely. All right? So try to find, like, go on Facebook Marketplace or something, or like on a news website with comments, or even like the news Facebook page. Go on Twitter or X or whatever it's called these days, and just search for some contentious topic, and you will find fallacies very easily. All right? It will take some digging though, but you will find them, and you're going to find examples of people messing up when they're arguing, because people like to argue on the internet. Okay? So there are a lot more fallacies than the ones that we talked about in class, and you're allowed to look for any of them. So like, here's a Wikipedia page with a bunch of fallacies. Make sure you understand the fallacy if you're trying to claim that it exists. But you can find any of those. You can look into computer science issues if you're having trouble about like which ones to find, but you can find fallacies about any potential topic. politics is usually the easiest one to find. All right, here are some hot topics if you're looking for things to fuel your searches. But your job is to go on Facebook or go on Twitter and like find fallacies. Find people making posts that are incorrect, that have fallacies in them. You'll figure out which fallacy it is. You'll analyze it, and that will be your essay. Okay? So here's what I want your essay to look like. At least 1,000 words. Here's the following structure. Like, make it an essay, please. Have like an introduction and a conclusion paragraph. But in the middle, the meat, I want you to find at least 5 fallacies, so at least 5 paragraphs, each having the following. I want you to quote a post from social media, like from Twitter. You can grab a screenshot if you want. That could be part of your word count. This is fine. And then I want you to analyze why that post has a fallacy in it. All right? So it's very easy to search for, like, maybe go to like a politician's Twitter or something and just hang out there. It's going to be very easy to find fallacies, I promise. And then you find the fallacy, you quote it, you analyze why it has that fallacy, and make sure you give its name, right? Because every fallacy has a name. This is a straw man. This is an ad hominem. Remember all those? So definitely give the name, because that's how I know you understand it. And that's going to be your essay. The only other requirement is that I think you can imagine how easy it is to find people saying bad things about each other on the internet, and that's an ad hominem fallacy, right? You can only use at most 2 ad hominem fallacies in your essay, okay? You have to find other ones for the rest, okay? But that is the bulk of the requirements. Does that make enough sense right now? So you're finding 5 fallacies on the internet, on social media. Yes? Yes, that's totally fine. If you find a video that has fallacies in it, just type out the quotes from it. That would be perfect. But explain why you find the fallacy, why there was a fallacy in that quote, and what kind of fallacy it was. That'll be part of the analysis, of course. All right? Let's see what else. Yeah, there's no, like, I guess you're citing technically these posts, but just leave a quote and like tell me their username or something. That's good enough for me. But that's the essay. Please read these directions a second time so that you don't mess up with anything. But that, I think we are all on the same page now. Here's like an example of something that you would find and talk about. Here's a good example I saw on Twitter. Whee! So there's a lot of fallacies on social media. Here's an example of a straw man fallacy. Let me see if I can zoom in. So I went straight to politics because that's very easy to find fallacies on. So here was the vice president making a post on International Women's Day a couple years ago. And she was like, I want to honor the women who for over a year, because this was mid-pandemic, right? I want to honor the women who for over a year have gone to work, often risking their health to nourish and protect us, doctors, nurses, teachers, grocery store workers, first responders, all these people. She was like, thank you on International Women's Day. And then this dude, Dave C., said, just the women? Guess that would be typical of you. I thank all who risked their lives for others, who risked life for others. And so this is what you would do for this essay. You would be like, here's the quote. This dude said this in response to this. And this is an example of a straw man fallacy. So you name the fallacy and you say why. This is a straw man fallacy because this person is putting words in the vice president's mouth. The vice president is trying to acknowledge women because it was International Women's Day, and the vice president was not saying anything about the contributions of men. She was not trying to belittle men or anything like that. She was just trying to point out that on this special occasion for women, we want to highlight their efforts during this pandemic, and that had nothing to do with how she felt about anybody else who risked their lives. Does that make enough sense? That would be your analysis. Something like that. You'd say, why are their words being placed in somebody else's mouth? Because this was not what the vice president was talking about. This is something different. That's not the same argument anymore. Okay, so that's a straw man fallacy. It's trying to bash down an argument that the vice president was not even making. Okay, trying to say that she said something that she didn't. Okay, that I think is what I wanted to say. Any questions about that? So you do that 5 times, and that's your essay, more or less. Yes. That is one of the lectures. It has a name at least. So let's see. Let me scroll back. Fallacies. It was lecture 12. So just go to that one. Look at the PDF. But there's plenty more fallacies where that came from. There's Wikipedia as well. So take a look at this page too. Yeah. Any other questions? So you got 2 weeks to do this. A lot of your 1,000 words will be the quotes from the articles, or not the articles, but from the posts. So that should be helpful. But yeah, definitely start early though, because it's going to take some time to find these on the internet. Yes. Yeah, you can just like give me their username or something. That works for me. Some way so that I can find them, making sure that you're not like making them up. That's all I need. Yeah. Yeah. Thank you for your questions. I think that's everything that I wanted to talk about.
Okay. See you then. Because I'll have to meet with you.